Welcome. So you just done your training and you've learned a little bit about the refrigeration cycle. Sometimes that's called the vapor compression cycle. And you've learned probably about heat loss and lots of things are probably inside your head at the moment. But I wanted to take you back to something very important, and that's heat. So as heating engineers, there's a great advantage to understanding heat. Now, one of the biggest things to understand about heat is it moves at different speeds. The sun is where we get our heat and light, and we all know that there's something called the speed of light. That's a constant speed. I can never remember what it is, but it's a constant speed. Heat is different. It moves at different speeds. So whenever you think of heat, just flash these images up in your head just to get the idea that it moves at different speeds. Now, why does it move at different speeds? What's the driving force to create these different speeds? Well, it's all to do with the temperature difference between 2 points. So what are our 2 points? Well, in the home, we tend to heat our homes, let's say, to 21 degrees. So the difference will be what's outside. So if it's -3 outside, the difference between 21 and -3 is 24. If it was 9 degrees outside, the difference between 21 and 9 degrees is 12. So that difference is what drives and creates all these different speeds of heat. And it's the same with radiators. So that's where you're pushing heat into the home at different speeds. So the average temperature inside your radiator is somewhere between the flow temp and the return temp. That gives you sort of the average temperature in your radiator. And that temperature and the room temp of 21 is what pushes the heat into the home. So if your home is actually, let's say you set your home for 18 degrees rather than 21, your radiators become more powerful because the difference in temperature is greater. Now I use this to help illustrate that. So don't worry about the numbers to start with. I'm not very good at maths. I only know this little bit. So, if this video helps you, some of you might get this straight away. Some of you might need to watch the video a couple of times. But I use this seesaw analogy. We all instinctively know what way that ball's going to roll. We know it's going to roll from the high end to the low end, and that's exactly what heat does. It moves from the high end to the low end, the hot temperatures to the low temperatures. So if you've got your home inside at 21, it's going to move outside if the temperature outside is colder. If it's a hot summer's day and the temperature outside is hot, the heat is moving in. So heat moves from hot to cold. We can also see from this seesaw that if there's a greater difference in height, a greater difference between the high end and the low end, the ball will roll quicker. And that's the same thing with heat. It's this difference. So obviously with the seesaw, it's a difference in height. We could say delta H. You might hear this word delta. Sometimes it's a little triangle. The symbol for delta is a triangle. It just means difference. And then the letter after it. So delta T, T stands for temperature. And that's what we tend to use. So on the left, I've got these things. These are the indoor temperatures. That stays the same. And obviously here we've got the outside temperature that's changing. It always changes. So that means the temperature difference is always changing. So the speed of heat actually leaving our home is always changing. And that means we should actually push heat into the home at different speeds. And this is where we get this whole idea of low temp heating. And low temp heating, any home can be heated with low temperatures, and we'll talk about that in a minute. And when I say any home, I mean any home. It's because you only have to drive heat into the home to match the speed of heat leaving the home. And that's where that's one of the second video we'll talk about why the condensing boiler got invented. A lot of people think it was invented to sort of capture more heat that ends up going up the flue. That's not why it was invented. So we used to do heat loss calculations. Engineers haven't been doing them, and that's not their fault. It's because we had an industry that liked people to sort of put boilers on the wall, and we've obviously had the combi boiler came around. Obviously we needed a high powerful boiler to give you the combi boiler is actually a centralized instantaneous hot water heater, so you need a lot of power in it to sort of so the hot taps run hot. So we just tend to put these things in, and heat loss calculations sort of started to not be used or become so popular, and obviously now with heat pumps we need to be sizing the home. So again, don't get too bogged down with the numbers here. We've got the indoor temp, and again here we've got the outside temp. So that's always changing. The outside temp's always changing, which means the difference between these two temperatures is always changing, which means our heat loss is always changing. Now when people do a heat loss calculation on a home, what they're actually doing, they're working out this one. They're working out how quickly will heat move through the home on the worst day of winter. Now, we can't actually pick the worst day of winter. The average temperature across the UK is going to be around about 7 to 9 degrees. Obviously it changes depending where you are. Up in Scotland it's going to be a lot colder. But that's the average temperature of winter. Now the average coldest day of winter across the UK is -3. Now again it changes. So up in Scotland it's going to be around -5. In London it's about -1.8. But for the whole of the UK the average is -3. So what we do when we do a heat loss calculation, we're actually trying to work out, well, how quick does heat move through this particular home when it's -3 outside, which is going to be a difference of 24, because we generally heat homes up to 21. How quick is heat going to move through that home when it's -3 outside? Because if we know that speed, that's the speed we have to push heat into the home at. Now, lots of people get heat and temperature confused. They're kind of, they've got a massive relationship, but they are two different things. If you want to get into the nitty gritty of it, temperature is the zero law of thermodynamics, and heat, which is energy, is the first law of thermodynamics. And if you really want to get into it, second law is entropy. So we work out how quick heat leaves the home when it's -3. Okay. And so we now know how powerful our rads have to be to push heat into the home at the same speed it's leaving. Now, when I say speed, we're all used to this thing here, aren't we? Kilowatts, watts. We're used to that term. Now, watts has time built into it. So 1 watt is 1 joule of heat per second. 1 joule of heat moving per second. 1 kilowatt is 1 kilojoule of heat per second. Now you could say it another way. You could say 1 kilowatt is 1,000 joules of heat per second. So when we talk in watts, we don't tend to talk in joules per second. Actually, if you look at some of the older boilers from the 50s, their boiler plates did actually have BTU hours, and they also had this joules per second. So I tend to use joules per second because it helps people remember that things are moving at speed. Like a car be miles per hour. When you say per time unit, per second, we associate it with speed. And I think sometimes when we use the word watts, we're forgetting that. Watts is obviously the unit of measurement for power, but it's got that seconds built into it. So as you can see, if we go down, I like to always use this 9. I should have actually coloured it red. So we know that across the UK it's going to be -3 is what we design our outside design temperature. So that's the difference of 24. Half of 24 is 12. Here we go, 12. So 9 degrees, the difference between 9 degrees outside and 21 is actually half. So if it's 9 degrees outside, now that's pretty cold. You're going to wear your scarf, your coat, your hat maybe, but it's half. The speed of heat leaving the home is halved. And what that means is we only should be pushing heat into the home at half the speed. And unfortunately, that's not been happening. And that's what the next video is going to be talking about. I hope you enjoyed this.